Good morning, statics class. This is ENGR 214 ampersand. This is winter quarter 2020 at Bellingham Technical College, and this is a recorded lecture for the method of joints truss analysis. This is picking up from our last live lecture on campus where we went over the definition of a truss, basically a structure composed entirely of two force members, usually something in the real world that's approximated by hinges or a fairly flexible relative to their bending moment cross-section or capabilities cross-section or flexural modulus in the members. So we'll have semi-flexible hinges or true hinges that can't support moment. So and that's again the whole concept behind a truss is two force members, so generally you will approximate that in the real world when you don't allow them to support moment. So this is the method of joints is the simplest and most reliable way of determining the forces in all the members and the supports. And I'm going to run through the definition here and step through the example here 4.1 that we started the last time we had a class meeting. So to do the method of joints, usually you will start by finding the support reactions by doing an FBD of the entire truss, putting it in static equilibrium and solving for the support reactions. And this will always be possible if the truss is simply supported, which means that in 2D anyway, you will have an X and a Y force applied by one of the support hinges and then just usually a Y or an X supplied by the other. So that would give you three unknowns. And in 2D you will have three equations of equilibrium, so that will give you the support reactions. Depending on the way the truss is being supported, that might not always be possible, but generally it will be. Regardless, once you have that done, or prior to that, you will isolate one pin, write the equations of equilibrium, which in 2D will just be the sum of the forces in the X and the sum of the forces in the Y about that pin, because the pin cannot support moment. If you have a space truss, then you'll have three for each pin. Sum of the forces in the X and the Y and the Z, just one more equation to solve, and that will give you 1, 2, or 3 of the forces in the members that intersect at that pin. And you will just go through the truss and repeat as needed until you've solved the truss, until you've found the forces in all the members. Generally speaking, depending on the truss design and depending on how many members intersect at any given pin, you'll very likely be able to solve for the forces in each of the members with each pin FBD instead of conditions of equilibrium. That won't always be the case. Sometimes you'll have an extra one, and in which case you'll end up just carrying that unknown over into another equation for another joint and solving it there. So as you can see, this is setting up to be a big system of linear equations and is in fact one of the reasons why the method of joints is typically solved the same way DC electric circuits are solved with Ohm's law, linear equations, with a method of matrices. So looking at our first example, you can see we have a simply supported truss. We have a hinge support at A, where we can apply a force in the X and the Y. And then we have a roller support at B that's only supporting vertically. So we have A sub X and A sub Y and then just B sub Y. We have our truss members, and then we are applying an external load vertically of 1 kip at D, vertically 3 kips at E, and horizontally 2 kips at C. And then we're given enough dimensions that we can determine the angles of the members at each of the pins. So if I were to approach this, my general rule is whenever possible, determine the support reactions first. And that makes it a lot easier to give me a starting point for my first joint, and it automatically gives me a number to check against when I get to my last joint and I have a check. So I have unmoored the truss from its hinges here and I'm looking at just the supports coming in from, the support reactions and the forces coming in from outside. I'm not looking at cutting across and isolating any joints yet. Pardon here for the pause, just making sure that indeed we are capturing the main screen before we go on 45 minutes of lecture and you're not seeing anything. Okay, so back to equations of equilibrium for the whole truss. This is the only time that we'll end up using a moment equation. So given that I have two unknown forces at point A, I'm going to take the moment about it. And so I don't end up having any moments due to a sub x and a sub y, but I'll have a negative moment from the 1 kip force, a negative moment from the 3 kip force, and a negative moment from the 2 kip force. And so in this case I actually wrote out the full cross product. I could have used geometry and just found the actual offset r distance from each of these forces being directed vertically or horizontally, but I did have the triangle directions, so I used the cross product in this example. So in the case of force number 1, I knew I was 3 feet in the x and 4 feet in the y from the point of application, and I had a 1 kip, I've skipped the units in this expression, downward force in the j direction, given my j and I. And then I'm going to add the moment from this 3 kip force. So my radius from point A to the 3 kip force is just 6 feet in the I hat direction represented here, and then my 3 kip force is pointing vertically downwards, so we have a -3. My 2 kip force over here, my radius to that 2 kip force would be 6 feet here, and then 3 feet to the midpoint of that triangle, and then 4 feet up. So that's 9 feet across, and 4 feet up is my radius vector, and then the 2 kip force is being directed positively in the I hat direction. All of that rotation is being balanced by the rotational moment being given by my support reaction, vertical support reaction at B, and that is 12 feet in the horizontal direction from my moment point A, and of course it's being directed upward. So when I solve, I multiply out all of those cross products and solve, I find that I have a support reaction at B, not surprisingly upward, of 2.42 kips, and then I plug that back into my sum of the forces in the x and sum of the forces in the y, and I get a sub x of 2 kips, which is balancing just this 2 kip externally applied force, and 1.58 kips for the vertical y support reaction. Okay, so with my support reactions at A and B, I'm prepared to start into my method of joints. So I'm going to start at pin A, and here's where I will invoke the geometry of the members. So at this point I don't need to see the truss anymore except to set up the geometry of the member intersection for each joint. So I'm now just kind of isolating pin A. I'm applying my vertical and horizontal support reactions that I determined from the whole truss FBD, and then I am representing the effect of the forces in members AE and AD, which I will go back up and refer to. Here's AD and AE. I'm representing those just with forces. And because the members are 2 force members, those forces are directed along the direction of orientation of the members themselves. So I have this theta angle to the vertical for member A sub D as 36.87, which I got from this right triangle here. And trusses are full of right triangles, so that makes it a lot easier. So all I have to do now is write the equations of equilibrium in the x and the y. So I have a sub e in the x, balanced by the x component of a sub d, which is total magnitude of a sub d sine theta, and then I have 2 kip support reaction being applied at A in the negative x direction. In the case of sum of the forces in the y, I have negative a sub d cosine theta downward being balanced by 1.58 kips upward from the support at A. A note about direction. I have assumed that the member A sub E is pulling on the pin. If a member is pulling on a pin, the pin is pulling back on the member, and that means the member's in tension. And when I solve these two equations and I get the values of the forces, the magnitudes of the forces in AD and AE, I have to note the direction they are, and I use a notation that's specific to the member itself to denote direction, and that makes it easier to port that force from pin to pin. So rather than indexing direction relative to an absolute coordinate system outside of the truss, I start indexing force direction within the member to the member itself, denoting whether it's in tension or compression. So since A sub E is pulling on the pin and the pin is pulling back on the member's in tension. So the standard notation for that is a T or a C with a circle. And you'll see that in every statics book and possibly on some engineering drawings. So we see A sub E has 3.185 kips tension and A sub D has 1.975 kips compression. So I have now gotten all the information I can from pin A, and I'm ready to move on to the next pin. And as I march up the truss, I can jump to any pin I want, solve what I can, and then go back and solve for the unknowns. But it tends to be easier if you flow from pin to pin and you carry along the information that you just solved for from one to the other, and you increase the likelihood that you will solve immediately for the forces for all of the members that intersect at that pin. Again, if you don't, no problem, you can come back and get it. We'll talk later about truss determinancy and looking at the number of pins and members and relating that to whether or not we have the same number of equations as unknowns, and whether we can actually solve for a single force in every member. But assuming that we do, and that's the case, we don't necessarily have to get the force in every member from each and every pin set of conditions of equilibrium, but it's easiest if we do. It's a little bit less math and less chance of error. So we're going to move from pin A up to pin D and do the same thing. Okay, so we've got here's pin D and I'm FBDing it. I have 1.975 kips coming upward from member AD. Remember, it was in compression, so it's going to push on pin D. I have a 1 kip downward, vertically downward applied force. And then I have the horizontal force for member DC and another force at an angle theta for member DE. I'm assuming that both DC and DE are in tension here. Chances are one of them isn't, and that will be shown simply by having the magnitude of the force for that member come out of the equations of equilibrium with a negative. And so that means negative relative to the direction it's drawn, and once I determine its orientation relative to itself, I'll just drop in a T or C. So we'll start with equations of equilibrium vertically in the y direction. I have -1 kip plus the vertical component of my force from member AD, which is 1.975. So I have 1.975 kips cosine theta, respecting my geometry, and then I have minus force in member DE times cosine theta right here. That all has to equal 0, and that gives me the force in member DE as being 0.75 kips in the direction shown, which is pulling on pin D. Pin D is pulling back, which puts member DE into tension. So I denote that with the circle T. Do the same thing with the sum of the force synthesis in the X, and you can see I'm picking up the sine component now of the 1.975 kips coming from AB, and my force DE balancing force DC, and I get a negative for my force DC. Well, I'd assumed that it was in tension, so negative means that it must be going the other way, which means it's in compression. So now I've picked off the forces in 2 more members. Okay, now I'm going to move to pin E, which is down here at the bottom, where I have 4 members intersecting at once, and I have my applied load of 3 kips. 3 kips being applied at a pin, which is the only place you can apply loads with a truss. Otherwise, we'd be putting our members into bending, which is not allowed. They cannot support it. Okay, FBD for pin E. So we have we have two that we're carrying over. We have DE, which we just solved for at the 0.75, and that's positive, shown here in tension, and the 3.185 for AE that we solved in our joint A FBD. We have a member EC coming off at angle theta, EB coming off on the horizontal, and then our applied load of 3 kips. So we'll sum the forces in the X. We get negative 3.185 kips, subtracting 0.725 sine theta, in this case sine of this angle, the way it's drawn denotes the horizontal component. We have the positive EC sine theta and then all of EB, pointing here in the positive direction. That's all equal to 0. I can solve that for EC in terms of EB. Can't get them both out necessarily, but with the sum of the forces in the Y, I can get EC directly. Because we only have 3 kips going down, we only have one unknown in the Y direction. So I can plug that back into the X, and I can get both EC and EB. They are both positive in the directions drawn here, and I drew them assuming they were in tension, so I note them both as being in tension. So now I'm going to use that information and the information for member DC, and I'm going to move over to pin C, and I'm going to repeat. This is quite the repetition. These are very, very long problems, so be sure that you leave plenty of time. So for member C, or joint C, excuse me, I have the compressive force from member DC coming in on the horizontal, and that came out of my my pin D FBD. I have 2 kips positive horizontal applied load being shown here, and then I have the force that I just solved for EC, 3.03 kips tension pulling downward, and I am assuming my member CB is in tension, drawing it that way because I can make some assumptions about equilibrium in the Y. If I have 3.03 kips pulling downward, given that these other 2 forces up here are only in the horizontal, CB really has to be in compression because it's going to provide the only force in the Y balancing upward. So I go through again the equations of equilibrium. The horizontal components of my 3.03 tensile kip force and horizontal component of CB, and then these upper 2 horizontals have to balance, and that's going to give me, that will actually give me in a single shot the magnitude of CB, and we find that it is indeed balancing, and it's at 3.03 kips. That's sort of a bit of a tautology. We can check it. That becomes a check in the vertical. So we actually solve for CB with either the vertical or the horizontal, and then we can use the other orthogonal direction as a check. So we start actually getting a check equation out of pin C, which is nice. And now we're going to move to pin B down at the rightmost horizontal support, and its entire set of equations of equilibrium should be a check, because at this point we should know the support reaction coming up at B from the B supports, and we now know all the members. Force directions. So if we just write an FBD and we slap all those numbers on, and then we see, do they sum to 0 in the X and the Y? And we see that they do. So we have, I can't get my pin notation right. We have CB coming down at angle theta, 3.03 kips, and remember it was in compression, so it's pushing. We have BE at 1.82 kips tension, and we go back to our original whole truss FBD, and we see we have 2.42 kips coming up. That came from our very first FBD. And we write our equations of equilibrium with those, and we see that yes, indeed, they do check within reasonable round-off error. So we have now solved for the force in every member of the truss. We know the support reactions, and we have checked it with our one redundant equation, and in doing so we have done what we call solving the truss. We now know the forces in every single member and the supports. And if we were in the real world, we would now hand this off to the realm of strengths and materials, and we would look at what materials we had and their properties and check for things like deflection and fracture. But these starting points of loads would be essential for any further action, so everything starts with statics. And we are going to end the lecture right now and record another with some more examples of other trusses with method of joints.